Hi everyone, and welcome to the section 5.7 video. So in this section we're going to be going over a few additional techniques of integration. And so just to give you a quick list of what's in this video here, we're going to be talking about a few different things, and they break down into three categories. So the first one is often called trig powers. Okay, and so what we're going to do here is we're going to be tackling integrals where there are powers of trig functions. And we're going to see that there are some very common substitutions we can use, so going back to u sub, that we can actually use because we can be real tricky and use some trig identities. So the trig powers are usually going to involve a u sub, not always, but it's common, and then also a trig identity to help us get ourselves into the right form. Okay, so that's trig powers. The second one is trig substitution. Okay, so this one's going to break down into three things. We're going to have integrals where we have a squared plus x squared, a constant, that's not zero. Or we're going to have things that have something like a squared minus x squared. Or we're going to see we have integrals with x squared minus a squared in them. Now, not every time you see this you just immediately jump to trig sub, because we still have u sub and we still have integration by parts, which could work and might be simpler. But what we're going to see is that in a lot of these scenarios, these three specifically, there are specific substitutions, again, going back to u sub, that you can make that involve trig functions that just simplify radically simplify what you have. And you'll see why that's happening. It's because of the square root, and maybe you can almost kind of look at this and see like, oh, I think I see kind of where trig could come in. I'm squaring and adding numbers. Maybe that's kind of making you think like, okay, trig could be in here. And that's what's going to end up happening. And then the third one is what's called partial fractions. And this is a little bit different than the others because it deals with rational functions. And it's going to rely on the fact that we know how to factor, and we also know how to take a fraction and split it into two separate fractions that are added. Which I know is weird. You're used to the other way, right? You're used to doing things like 1/2 plus 2/3. I was trying to think of an easy one so I didn't mess up here, but well, 2/3 is easy enough, right? Like you're used to taking this and smushing them together, right, into sixths. So, right, that would be 3/6 plus 4/6, 7/6. We're going to use the fact that this goes both ways. We could take 7/6 and rewrite it in these two simpler fractions. That's what we're going to do with this partial fractions. We're going to take a rational function already like this, and we're going to break it into separate, smaller pieces. Because remember, if I integrate, right, if I integrate a sum, I can do each of them individually. So what did we just say? We're going to take a harder fraction made up of functions, rational function. We're going to break it into two simpler ones with addition here. And then when we do the integral, we get two simpler integrals. So that's what you got to be thinking about with what's going on here. So a lot in this section. Let's just kind of dive right in. Let's dive right into it. So go through here. And we're going to start with the power of trig functions. So there are three identities here that are going to be useful. This one, which actually is a hidden, like a secondary hidden one in here, which we'll talk about in a second. This one, this is one of the half angles, and this one is another half angle. Okay. This one, trickily, actually has other forms. So, you know, maybe I'm sure you've seen this at some point, but you can rearrange this formula to get at different types of trig functions. So watch what happens if I just take this formula and divide by sine squared. That's going to give me 1 plus cosine squared x over sine squared x. We're going to divide by sine squared over here. And this doesn't look very nice, right? But this is actually 1 plus cotangent squared equals cosecant squared. And so now I have a new, almost like a new Pythagorean theorem right here that allows me to take cosecant squareds and turn them into cotangents, and vice versa. So you could do the other way, and we'll see that in a little bit, where you divide by cosine squared, and you're going to relate tangent and secant, which is kind of cool. They're squares, actually. So that one's like a sneaky 3 in 1. These are just 1 in 1s. There's just this one and this one. And here it gives you like a rule when to use it. If the integrand contains even powers of both sine and cosine, we're going to use these. If you have an odd power, okay, instead of one of them, then you can use these, okay? Or if you've got cotangent, tangent, secant, cosecant, you're going to go over here. So it's not too bad. There's only actually 3 trig identities here. And this one, even though it's, multiple, it's really just from this one. So it's not too bad to, remember them and just get them again by dividing. So it's not like really you have to memorize all of these different ones. So this is what we're going to use. So let's just jump into a problem. Okay, so we've got down here sine to the 5th x cosine to the 3rd x. So what did I say above? There's going to be a u sub, and there's going to then be use of one of these trig identities. Now I see odd powers, right? So then that makes me think I should use this one. So because there's odd powers, I'm thinking I got to use this one. And so when I say I have to use it, like what do I mean by that? Well, there's 2 ways to use this. One way is to solve for sine squared. And what this does is it makes it so that I can take any sine squared I want forever and ever and replace it with a 1 minus cos squared. Or vice versa, right? If I get this, I can replace it with sine squared. Or I can solve for cosine. And so this gives me these 2 formulas I can use. And these are good. Forever and ever I can use these. So, okay, you're kind of maybe looking at this like, all right, so what? Well, I said there was going to be a u sub. So you're looking here for a function inside another. And the other thing you have to remember is that the derivative of that should also be in here. And so hopefully, it's not too bad to remember things like, oh yeah, sine and cosine have that, back and forth with their derivatives. So the derivative of sine, right, the derivative of sine is cosine. So maybe that's making you think like, well, wait a minute. Okay, maybe I could do something where like u is sine, right? Because then there'll be a cosine and I get to gobble that up with the du. So yeah, okay, maybe that can make sense. But the problem here is if you make u sine, it's like, okay, well, let's just try that substitution, right? U is sine. So let's give it a shot. So I'll rewrite it down here. U equals sine x, and then we're gonna take this integral, forget about the bounds for now, and try the substitution. So watch what happens. So we're gonna do the substitution. Integral of sine, that gets replaced with u. Okay, that's a lot easier. Okay, but then you got this cosine cubed, and so you're like, well, okay, well we did the derivative, right? So then we got cosine x dx. So that gets rid of one of them. But there's more powers here, so that's not going to work, right? I've got this extra, I'll write it up here. I've got this extra cosine squared hanging out. Because what we just saw was this cos x dx, that can get absorbed into du. But I got this cosine squared hanging out still. But wait, I just wrote down that cosine squared can be turned into sine. So, okay, well, let's try doing that, right? So we're going to rewrite the integral up here. Again, I'm just going to leave off the bounds for now. Sine to the 5th x cosine squared x, right here, becomes 1 minus sine. So I'm not even going to write it there. Let's just do the replacement. So again, there's a cosine squared because there's 3 powers. So I'm just pulling 2 off. And I'm going to replace it with 1 minus sine squared. Okay, that's just because of the Pythagorean theorem. Then there was the extra cosine here. All right, so before we were like, uh-oh, what do we do? But now, let's retry this substitution. Let's retry. Integral u to the 5th 1 minus u squared, and then cos x dx becomes du. Well, would you look at that? We needed, because we chose sine here, we needed a single copy of cosine, right? A single copy of cosine to get absorbed into the du, which means any extra copies of cosine, we've got to somehow turn that into sine so we can u sub it away. And we can do that because of the Pythagorean theorem. And hopefully you'll also see immediately why odd power is so important. If this was an even power, cos fourth, we don't have this single cosine here to pop out. If it's even, then these come in pairs, and you're going to end up with, if this was to the fourth, there's no way to pull off one cosine and use this method, because this is 2, not 3. Even if it was 4, that would actually be okay, because you could just do it twice. But we need this to be odd so that we can pull off a single cosine for the du. That's very important. Okay, so from here, we know how to do this. Let's just do a little algebra here. U to the 5th minus u to the 7th du. Okay, do the antiderivative. Add 1, divide. Add 1, divide. All right, and now we have to remember what's going on here, right? We actually do have bounds. So again, like we talked about way back when, you have a choice. You either change the bounds to u's, or you change back to x's. So it's really fine. Remember, we get these limits here that should be written in u's, but we're not going to do that here. Let's just go back to x's. Again, it really isn't a big deal which way you do this. So this is sine to the 6th x over 6 minus sine to the 8th x over 8, and it was from pi over 2 to 3 pi over 4. Okay. Awesome. All right, and now we just have to plug in. All right, so let's do some plugging in then. So again, remember, this first, then this. So this is sine to the 6th of 3 pi over 4 over 6 minus sine to the 8th, 3 pi over 4 over 8. Okay, and then minus, then we plug in the pi over 2. Sine to the 6th pi over 2 over 6, and then minus sine to the 8th pi over 2 over 8. Okay. And then we just have to remember some of our sine and cosine values. So, at some point probably you had the unit circle and all these different values to memorize, right? And so the big ones were what? Pi over 6, pi over 4, 3 pi, or pi over 2, pi over 3, 0, pi, list goes on, all right? So let's see if we can remember this. So sine to the 6th, who cares about the 6th for a second? Sine of 3 pi over 4, that's in the second quadrant, right? So what that's going to end up being is for cosine negative root 2 over 2, because you're second quadrant, but we're sine, so it's root 2 over 2. So this would be root 2 over 2 to the 6th over 6 minus root 2 over 2, because again, same thing, I'm plugging into the 8th over 8. Okay, minus, and then pi over 2 for sine, right? Well, pi over 2 is a nice one. That's just 90 degrees. So that for sine is just 1. So 1 to the 6th over 6 minus 1 to the 8th over 8. Okay. And so then, at this point, you can keep kind of going through and trying to simplify stuff, blah, 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 or you could just plug into a calculator and see what you get. So let's just plug in a calculator and see what we get. So that gives me a final answer of negative 11 over 384, which I obviously did in my head. Can't prove I didn't. And there we go. We've got it. All right, so recap. What did we do? Odd power. So we're going to use some form of the Pythagorean theorem. We figured out that if we let u be sine, then we can absorb a cosine just using the du. But in order to do that, we have to pop a cosine off here, which left us with this cosine squared. that's where the Pythagorean theorem comes in. We get to this much nicer antiderivative to do, and we did it. There you go. So let's try another one. This one, might look a little scarier because you're not used to sine, or you're more used to sine and cosine, things like that. But it actually gives us the substitution here to use, which is pretty nice. So u equals secant x, so du equals secant x tan x. So we go over here and we're like, what? Because I see a secant, so cool, that can be u, but I don't see a secant tan. I do see a tan. So let's just, reassess. Okay, if I just do this, tan secant, right? Then look, I do have du. This whole thing could become du in this substitution. Awesome. But looking over here, this isn't secant, so it doesn't just, I can't actually get rid of it using, or turn it into u's using this. But what do we know? We know that cos squared plus sine squared equals 1. And how do I get tangent? Well, that's sine over cos. So why don't we just divide everything by cosine? Let's see what happens. Okay. All right. So we get 1 plus tan squared equals secant squared. Oh. So that means tan squared actually can be turned into secant squared minus 1. So, okay, great. I see a tan squared. I need secant so that I can actually do the u sub. So, all right, great. This actually just becomes the integral of secant squared x minus 1. And then this whole chunk here, I'll rewrite it in x's, but remember, that's going to turn into our du. So, just to rewrite it, u is secant. Du is going to be secant x tan x. And when I do the substitution, bring these together, which I'll actually do over here for space issues. We bring these together, and we're going to end up with the integral of, well, this is u squared minus 1. And then this whole chunk just becomes du. And whoa, that is a much nicer integral. We can do this without too much trouble. Add 1, divide, right? Add 1, divide, but that just becomes u. And then we're going to do that from, just kidding, this is an indefinite integral. So we're going to plop on our plus c. Okay, and then go back to your x's. So this is secant cubed x over 3 minus secant x plus c. Boom. Done. So hopefully that's really not too bad to use. Right? We just have to use that same formula, pop one out, rearrange things algebraically, get yourself a du here that makes sense, change whatever you need so that you can get into the right u's, and you're good to go. All right, let's start looking at trig substitution. So we've got 3 options here. Form a squared minus x squared, a squared plus x squared, or x squared minus a squared, all under the radical. Okay? So what we're going to try to do here is use trig, a trig substitution, and the whole point of these substitutions, no matter what the situation is, here's the whole point. The whole point is, if I can get something that looks like this, right, I can simplify. Right? Greatly simplify this. Okay? This is the entire point. I'm trying to get a square, a thing squared under the square root. That's it. So that's what your goal is. All right. So let's check this out. We're going to do something a little different because you're seeing here a bunch of square roots, right? But for this problem, we're going to still use the trig sub idea, but we don't actually need the square root to do cancellation and kind of get where we want to go. This is a pretty nice one that doesn't need it. But it still shows you everything that goes into doing one of these problems. So it's still a really great example. Now, I think this is a really good example to try seeing if you can do something like this on your own. Okay? Now, I'm going to go through the whole derivation for you, but I really think it's a good idea. Just see where you're at. See if you can pick up on some of the same things I'm picking up on. So one way to do this is just try it now. If you're not really sure where to go with the trig sub, okay, I'll start giving you some thoughts and hints and leading you in that direction. Just try pausing it and seeing if you can take the next steps. Pick up on the thread that we're following and go the rest of the way. All right? But we're going to do it right now anyway. So if you want to pause, try. Just keep pausing as we go through and do new things. So, okay, here we go. I'm looking at this, and I see a squared plus x squared. Now, I mentioned before that we want to try to make this multiplication in here, because if you can make this something squared, you're going to have a better time with the square root. And that still works on the bottom here. This is a sum down here, which is really not easy to deal with fractions. But if we can turn this into multiplication, it gets better. So, okay, there's a couple ways to be thinking about this. But one way that you can immediately try thinking about this is, well, okay, if I just get an a in here somehow, then I can factor the a squared, and that'll give me multiplication. That's good. Okay, so maybe I want to do some kind of substitution where there's an a in there. All right, I need a little more than that, but it's some start. And remember, a is just a constant. So okay, so what kind of trig subs do I have? Well, remember, we've got the sine squared theta plus cos squared is 1. We've got all the other different ones we can do. Tan squared plus 1 equals secant squared. And then we also, remember, have 1 plus cotangent squared equals cosecant squared. Okay, so thinking about it this way, right? If I can make a substitution where I see this, see how there's a plus, like a number plus a function, right? That immediately makes my eyes go to these two, because I get a number plus a function squared, right? So a number and a squared thing turn into just one function. Oh, that would be better than having the plus sign, right? So how do I make that happen? Well, I've got the plus and the number. So, okay, that's good. But what I don't have is a tangent. So I'm going to write that down. I'm going to do tan theta here. And so x squared is a squared tan squared theta. Okay, so just try. Give it a shot. Just focus on the bottom here. What happens if I did the substitution with the bottom? Well, I'd end up getting a squared plus a squared tan squared theta. Okay. Now, I can factor out, like I said we might want to try, a squared 1 plus tan squared theta. Okay. And then we know, like this was kind of part of the goal, was the 1 plus tan squared. That's secant squared. So, okay, the bottom actually just becomes a squared over secant squared. And look at this. Goodbye addition in the denominator. We're able to get rid of it. So that's a really great step that we took. Now we just have to figure out what happens with the rest of this, because remember, we got to deal with this dx. So we got to think about this a little bit. We've got x equals, so how do I get dx? Do the derivative. All right, what's the derivative of this with respect to theta? Well, a is a constant, so it stays. And tan, the derivative is secant squared. Okay. So what does this tell me? Dx needs to be replaced by this. So, okay, I can do that. Now that seems like it's making it a little bit more complicated maybe, but we'll see what happens. So, okay, take a ride over here too. And why not? Let's keep it going. And we could drop the d theta over here. Oh, look at that. Boom, boom, boom. Huh. Well, that's pretty nice. Okay, well, we're just going to roll with this. It's looking nice, so don't, we're not going to question ourselves. Oh, how'd that little a get down there? Okay, it can just hang out. That's fine. So a is a constant, right? So this is 1 over a theta plus c. Wow, look at that. That's a lot nicer. But remember, when we're doing substitution stuff, we don't want thetas, we want x's. So okay, I'll just go backwards, right? Oh yeah, this theta here. It's tucked inside the tan. So we got to solve for this. So we have to now take the step of saying, okay, we have this, we got to solve for theta. So divide the a, you get your tan theta, okay. And then we have to get rid of tan, but that's not too bad because we could just use arctan, which you can write as tan inverse if you prefer. That's fine with me. All right, so that's what theta is, so let's do it. Let's bring these together. We get 1 over a arctan x over a. Ta-da! There we go. So if you ever see this integral, 1 or whatever number over a squared plus x squared, where a can be any number, you immediately know, oh yeah, the antiderivative of that is 1 over a arctan x over a plus c. All right, so that's trig sub. It's taking in this thing that kind of looks trig-like because they're squares of things, you're adding them, and finding the right substitution of a trig function and the right property here, trig property, that allows you to do a substitution. It's a little weird because we're used to the new variable being out here, right? I get that that's a little weird. U sub, right? U is here, and then we've got some function of x usually. We flipped it this time though, right? The new variable is actually in here inside tan, and x, the old variable, is the one out here by itself. So that's flipped. I know that's a little bit weird, but you see what happens. We do this, we can use a little algebra, get ourselves one of these trig identities to do simplification. We get to a much simpler integral, and then we got to do a little work here to undo to get back to theta, but it's not too bad. Done. So all right, hopefully that's not too terrible to do. The rest of these are similar, right? Each of them has their own specific substitution you're going to do. Hopefully from that one isn't too bad to see that this one will be tangent a tan theta. We'll go with this one. And then, the others have their own. So, for example, this one will be connected to using a times secant theta. And this one is going to be connected to you using a sine theta. So this form use this form use this form use this. Not too bad. All right, let's keep on going. So lastly, we have partial fractions. So partial fractions, kind of a different beast. We're just lumping it into this section because it's just a new type of thing to do. But partial fractions has us dealing with rational functions. So remember what I had said above. I see 7/6. I think of that as 1/2 plus 2/3. And you're probably like, what kind of weirdo sees 7/6 and thinks of it as 1/2 plus 2/3? Well, a weirdo who has done a good amount of partial fractions, which is going to be you soon. So the whole goal, look at this rational function. Oh, it's terrible. Boo. Well, what can we do? We can break this into two simpler fractions. Okay, and it all starts in factoring the bottom here. That's all where this starts. So that's our goal. We got to factor this. So step one here is factor. We can do it. So, okay, what do we need? We need two numbers that multiply to 6. All right, and when we add them, we get -5. All right, so you just do all the different options. You got some 2s and 3s here, some 1s and 6s, okay? But we got to think about this. This is positive, so they both have to be negative, right? Or they both have to be positive. Two options. But I add to a negative, so that tells me at least one of these numbers needs to be negative. This one tells me they both do. So I'm going to go with 2 and 3. I'm going to say A is -2 and B is -3. Add these, great. Multiply these, great. Okay, so what am I saying here? I'm saying this is the same thing. X plus 2, X plus 3. Multiply this out, awesome. We're going to get the same thing here. Okay, so now the goal is to rewrite this as some number A over X plus 2 plus some number b over x plus 3. This is the goal. If we could do this, just think about this. Whoa, this integral is going to be way easier to do, right, than this one. Way easier. So we got to get there. Okay, how do we do this? Well, how do you combine two fractions? You got to get a common denominator, which in this case, the easiest way to do is these multiplied. So it's just like I did the other example, right, with the 2 and the 3. Well, I multiplied the two numbers and then multiplied the opposite number up here. So what does this look like? Let me write it out. A times x plus 3 plus b times x plus 2 all over x plus 2, x plus 3. So what I'm doing there is I'm combining these two fractions to get to this. Okay. Now the process, you'll see in the process, we're actually writing way more than we need to. But I just want to show you kind of where it's coming from a little bit. All right, I have two fractions. Denominators are equal. Fractions are equal. What do I know? Well, if this is really true, I need just to focus on the top. I don't care about the bottom because they're already equal. So, what am I saying? I'm saying I need, and we're going to actually multiply this out as we go here, all right? So I need ax plus 3a plus bx plus 2b, so I'm just multiplying out here, to equal x minus 4. All right, well, we actually have a nice property here, right? X's all go together, numbers all go together. So this turns into two equations. Ax plus bx equals x, and 3a plus 2b equals negative 4. So, okay, all right. Two equations, two unknowns. This should ring some bells. I can do this. This one gets even simpler. I can do a little factoring. Watch this. A plus b, x equals x. So what's a plus b have to be? You could do it. A plus b is 1. So let me rewrite these. Two equations, two unknowns that I have to solve. Two equations, two unknowns. There's so many methods to do this. You do it in whichever method you like. There's the solve for one variable, plug into the other. There's the multiply them and add or subtract. There's the I know how to deal with matrices style way of doing this and reducing matrices, whatever. So we're going to, in this one, because it's not too bad, we're going to go with the multiplying a row and adding. So watch what we do here. We're going to multiply the bottom by negative 2. So that's 3a plus 2b equals negative 4. And we're going to hit this whole thing with negative 2. So let me put that in a different color. We're going to hit the whole thing here with a negative 2 on this whole thing. So that's going to give me negative 2a minus 2b equals negative 2. Now, we're going to add these two together. Let's see what happens. That's going to become, do a big plus sign, a equals negative 6. All right, that worked out pretty nice, right? The b's canceled, a's came together nicely, numbers did too. All right, now bring this back over here. Negative 6 plus b equals 1. B has to be 7. Okay, so we know A, we know B. This is a long process, so it's hard to get lost in it. So go back up here. Oh, these were just the tops here. So what do we say? A is negative 6 and B is 7. So my original integral becomes, there's a lot of space taken up here too, don't forget, becomes negative 6 x plus 2, and I'm going to separate them into 2 as well, although you don't have to. 7 over x plus 3. This now is me separating this integral in its more compact form but more complicated into this simpler one. And this one is real quick. Negative 6 natural log x plus 2 plus 7 natural log x plus 3 plus c. Boom, boom. You're going to end up seeing a lot of natural logs in these types of problems. So hopefully that's not too bad. All right. So go on to another one. Now, this one is trickier only because it's got more factors down here, right? So again, it's the same idea. This is some fractions smushed together. My goal, unsmush, desmush, whatever it is. So x cubed minus x is, let's factor x times x squared minus 1. This one's not too bad. That factors into a plus 1 minus 1. Okay. So 3 factors tells me I can separate this into 3 separate fractions. So what do I mean by that? Well, here's what I mean. This can be turned into, let's rewrite it all out, the integral of a over x plus the integral of b over x plus 1 plus the integral of c over x minus 3. I have separated this into 3 separate simpler fractions all added together. Okay? So, this is, I just add another factor down here, so of course this is going to get more complicated. And in problems I'm going to ask you to do, we're going to be focusing on 2 factors. But this is extendable, so I figured I'd just show you what this looks like to do. All right, so let's just kind of go through this one just so you can see it. But I'm going to want you to focus on just 2 factors alone. So, okay, just to kind of see this, let's check it out. So here we go. Remember how we do this. I need to hit A with the other factors. So this would be A, and then we know actually this is x squared minus 1. So I'm going to cheat a little bit and put those back together. Plus, and then B is going to get hit by this, which is B x squared minus x, plus C is going to get hit by x squared plus x. Again, it's just these 2 factors. Hit C. This needs to equal x squared plus 2x minus 1. Because the fractions need to be equal, and remember the denominators already are, so we don't need to worry about that. So what's this tell me? It tells me ax squared plus bx squared plus cx squared needs to equal 1x squared. Right? All the x squareds need to be equal. Okay, what about the x's? Well, there's no x here. So you don't need to put a 0, but I'm going to do it. There's a minus b on this x, right? And there's a plus c on this x, and that needs to be equal to 2. So again, just so you're reminding, these are the x squareds, these are the x terms, and then here we're just going to use I'll use a 1 here, but it's the constants. So that's a negative a, no b, no c, equals negative 1. And this worked out not too bad. We want to solve. We got 3 equations, 3 unknowns. But luckily, this one tells us a equals 1, right? Which we can then substitute into the top, which will give us 1 plus b plus c equals 1, which tells us b plus c equals 0, which tells me that b equals negative c. Now we can take this one, negative e plus c equals 2, and this one, and combine them. So here and here, getting comboed in. Okay, so then let's plug in. B is negative c, which means that c plus, because minus minus, plus c equals 2, 2c equals 2, c equals 1. That tells me from this equation that b equals negative 1. So 1, negative 1, 1. 1, negative 1, 1. So let's do this. 1 over x dx plus negative 1 over x plus 1 dx plus 1 over x minus 1 dx. All right. These integrals aren't too bad. Log plus, don't mess up here, almost there, minus log plus log plus c. Boom. Nailed it. So there you go. I know that was a very long video, lots of different, types of problems here, but hopefully, you practice the process a few times. It's not too bad. All right, so get some practice in here. Work on these, work on these, work on these. And of course, if you have questions, let me know. Stop by the Discord, send me an email. We can meet over Zoom, and I'll see you in the next video.